the answers for Test 1 Geometric Optics. Starting with question 1. The ray model of light and law of reflection tell us that the angle of the ray model of light and the law of reflection tell us that the angle of an incident light ray will be equal to the angle of reflection. Why does a mirror reflect a clear image while other seemingly smooth surfaces like paper do not reflect clear images? So, a surface like a mirror will be flat, relatively flat. And when an incoming light ray or incoming light rays strike the surface, they will be reflected off and stay parallel. So if they come in parallel, when they reflect, they will also reflect parallel to each other. On a rough surface, incoming light rays that are parallel will reflect in different directions. So, this here we call specular reflection. This here is called diffuse reflection. And diffuse reflection is a good example of how something works on paper or other seemingly smooth surfaces. The difference here is that paper on the microscopic scale is rough. And this causes all the light rays to reflect in different directions. And we call that diffuse reflection. So no clear image is formed because of that. For a mirror, a clear image is formed because we get specular reflection. And parallel light rays are reflected parallel. Or at least very, 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 very close to parallel. That was question 1. Question 2. To see a fish underwater, light rays must travel from the fish, through the water, then through air, and then finally into the eyes of the person fishing. For this question, assume that the lake this is happening on is calm and there are no surface reflections that make it difficult to see. So perfect conditions, basically. Part A. If the person is going to throw a spear at the fish, should they aim directly at where they see the fish? Yes or no? The answer here is no. If I answered no, explain where the person should aim instead. So, no, that was one of the 2 points there. The person should aim a little closer and deeper than where the fish appears to be. All right, so this is because, so if I have the surface of the water here, and this here is my normal, and over here is my fish, a light ray coming from the fish to the surface of the water will bend away from the normal because it is speeding up. So I have a person where that light ray reaches their eyes. So the person is seeing the fish. However, the person will see the fish over here. Because if you trace back this light ray, then the person's going to see the fish a little bit behind and a little bit above. That's where the fish actually is. because of the refraction at the surface of the water. Now, part B, if the fish was directly below the person, how does your answer change? So the way I've worded this, I basically tell you that it does change, so there is a change. The answer changes by saying that, yes, the person now should aim directly at the fish. Now this is because if I got my surface of the water and my normal and my fish and my person, the light ray going perfectly parallel to the normal. When a light ray is parallel to the normal, if we were to plug that into Snell's law, we get the sine 0 degrees as the angle between the light ray and the normal. We get that for both angle of incidence and angle of refraction. And we end up with 0 equals 0, so there's no refraction happening here. So because the light ray is parallel to the normal, it's perpendicular to the surface, no refraction happens at the surface here. If the fish swims far enough away from the person fishing, it will disappear from their vision entirely. Why does this happen? So the short answer here is total internal reflection. And total internal reflection occurs when the angle of incidence, theta I, is greater than the critical angle. So what this looks like with a drawing I got my person and my fish again. Now our incident light ray heading towards the normal and the surface of the water, it's at such a large angle here. So theta I is so large that the light ray, the angle of refraction is equal to 90 degrees or greater. And instead of refracting across the water-air boundary, it'll be totally internally reflected. So as the fish gets closer and closer to the person, the angle will become steeper and steeper until, the angle will become less and less and less until it's 0 in the case of part B. But in our case here, it is far enough away that the angle is large, very, very large, and total internal reflection occurs. So those were questions 1 and 2. Question 3. Draw 2 or more light rays to complete this ray diagram and determine the salt image characteristics of the image. So let's go ahead and start. Now, something I should have mentioned, but I did not, is that this is a mirror, a spherical mirror, where this backside is the non-reflective surface. Just to make it more clear. I should have mentioned that. My bad. But either way, the solution's still the same. So there's a couple different light rays we can draw. I'm going to start with one that is parallel to the optical axis, because that is how my ruler started. Sorry, page was jumping around on me. Awesome. So this light ray is parallel to the surface. Now, it will reflect through the focal point here. And if I trace back the virtual light ray through the back, it will continue along the same line and look a bit like this. So that's my first light ray. My second one will start by coming from the object, as always, but also in line with our focal point here. So like this. So still in line with the focal point. Now, opposite of the previous line, this one reflects back parallel. And I'm going to trace back the virtual light ray, just like this. Now, this is enough to determine where the image is going to be. It's going to be right here. Actually, let me try this. This is a new little feature. Boom. Beautiful. So that's enough to figure out where the image is going to be and to solve the problem. However, I'll show you the last line anyway. On a spherical mirror, any light ray that is going from the object and through the center of curvature will always reflect back through the center of curvature. So this here's our line. Oh, I should leave that there. All right, there's our line. And again, if I trace back the virtual light ray, they all converge on a single point where the image is. So, salt image characteristics, S is for size. This is larger than the object. Attitude, it is upright. Location is right of the mirror or behind. And type, this is virtual. We had to trace back the virtual light rays to create the image. The real light rays over here on the left, they diverge. They go in opposite directions and they will never converge. So we have the virtual light rays on the right-hand side that converge. So that was question number 3. Question number 4, when you want to see clearly underwater, you must wear goggles filled with air. If they fill with water, your vision becomes blurry. Why does the air trapped in the goggles being in contact with your eyes make your vision underwater clear? So, I'll draw 2 scenarios here to help illustrate my answer. This is a person's eyeball wearing goggles filled with water. And I'm going to draw, oops, not what I wanted. Okay. There we go. And another pair over here, filled with air. So, on the left, an incoming light ray that's going through the water on the outside will not refract as it goes through the water barrier. And as it enters the eye, you're going from a refractive index of about 1.33 to whatever the refractive index of the eyeball is. The refractive index of an eyeball is very close to water, but it doesn't matter for this question. You don't actually need to know it. So we know that we're going from 1.33 to the refractive index of the eye. Now, In the other case, we have a light ray. It's going to refract a little as it enters the air pocket here, but that doesn't really matter too much. What we're actually looking at is how it will refract when it hits the eyeball. So here we have a refractive index of 1.00 for air going to the refractive index of the eye. The difference here is that we are changing refractive indexes. So when going from 1.33 to the refractive index of the eye, that is not what the human eyeball evolved to do. This is not what the human eye is used to. It's not what it's designed to see. The human eye is designed to work when exposed to air. So, because the refractive index of the medium surrounding the eyeball changes when it's underwater, that changes how the light refracts through it. And if the light changes, if the way it refracts changes, then, of course, your vision is going to be a little bit blurry. The light will not focus the way it needs to focus. And you will end up with blurred vision, blurry images. You'll still be able to see a little bit, but it'll be blurry. So putting on goggles, getting the air contact with your eye allows it to properly reflect. So, in short, the change in the refractive index when the eye is in contact with water, I will say changes how the light refracts through the eye, blurring the image. So that was question 3 and question 4. Question 5. For the optical system in the diagram, calculate R2. The optical power of the system is 7 diopters, the radius of R1 is 20 centimeters, and the relative refractive index is 1.5. So the equation we're going to use is P equals n minus 1 over R1 plus 1 over R2. And I'm pulling that just from the back over here, this equation. Plugging in values, my power is 7 diopters. I got 1.5 for the relative refractive index. I'm told that R1 is 20 centimeters, which is 0.2 meters. And I'm looking for R2, so I will leave that as is. Simplifying, I get 7 equals 0.5. 1 divided by 0.2 is actually just 5, plus 1 over R2. Can't do anything with 1 over R2 just yet. I'm going to divide both sides by 0.5. This gives me 14 equals 5 plus 1 over R2. And I'm going to flip this around quick. So 1 over R2 equals 14 minus 5. I'm also subtracting 5 from both sides. I have 1 over R2 equals 9. And this is really just 9 over 1. I'm going to flip both fractions. R2 equals 1 over 9. And because R2 is a concave surface, it needs to be negative. Negative 1 over 9 meters. There was a little bit of confusion as to whether or not this should be a positive or a negative in the formula. When I first created this problem, I used a negative here, which made the final answer negative by default, which is why I had to force it to be negative just now in my solution. Please see the announcement about this equation. I just put one out today, October 8th. Please take a look at that. It explains the difference between both equations. Both are correct. They just are used with different... I'm blanking. They're created differently. They mean slightly different things. Basically, how you decide what is positive and what is negative in optics determines what equation you use here. For us, we are using one with the positive for us. So negative 1 over 9 meters was the correct answer, or R2 equals negative 11-ish centimeters, if you do the conversion. So that was question 5. Question 6, a light ray inside of a diamond with a refractive index of 2.42, so N1 equals 2.42, hits the inner surface at an angle of 20 degrees to the normal. So that means theta 1 equals 20 degrees. If the diamond is surrounded by air, which has a refractive index of just 1, what will the angle of refraction be? Looking for theta 2. So this is a Snell's law question, where we have a light ray going from one medium to another. And Snell's law is N1 times sine theta 1 equals N2 sine theta 2. Plugging in values, 2.42 times the sine of 20 degrees is equal to 1 times the sine of theta 2. I'm going to take the inverse sine, the arc sine of both sides. So I get arc sine of 2.42 sine 20 degrees equals theta 2. So theta 2 is equal to, now I don't remember what that is off the top of my head, but I have the answer sitting here beside me. You should have gotten something that rounds to about 56 degrees. And that was it for that question, that problem there. So that was questions 5 and 6. Moving on to 7. Now I'm going to quickly rotate my page. There we go. I'll rotate it back at the end. So complete the ray diagram, finishing the 3 light rays and drawing in the final image, and again list salt image characteristics of the image. So I give you the start of 3 different light rays. I'll go top to bottom. The top one. Now, I think this was probably the trickiest one. This one, if I hold up the ruler like this, I think it's clear to see that this light ray is in line with the focal point on the left side of our lens here, which means that if it's in line with the focal point, it has to refract through and end up parallel to our optical axis. So this light ray goes like this. Tracing it backwards, just in case we end up with a virtual image, I got my dotted line. Next, I have a parallel line to the optical axis, and just like the line before, this is kind of like the opposite, where I know this one will go through the focal point. So I will go ahead and trace back the virtual light ray. And I can see that they're diverging on the right already and converging on the left. So I'm already very confident that this is going to be a virtual image, but let's do the final one anyway. Final line, this is going from the object to the center of the lens. A line like this, a light ray like this, does not refract and goes straight through. But we can trace back the imaginary virtual light ray here. There we go. And here we have our new object, or our image, sorry. So here we have our image right there. And our diagram is now done. We've traced back all 3 light rays to find the image. It is clearly larger. It is upright. It is left of the lens, but more specifically, it is left of object and right of focal point. And the type is virtual. We had to trace back virtual light rays to create this image. The real light rays over here on the right-hand side, they are diverging. They're clearly moving away from each other. They will never meet. And we had to trace back the virtual light rays, see where they converged to get our answer. So that was number 7. I'm going to go ahead and rotate the page back to how it was. Number 8. This was the big one. This was the big one for this test. So, part A, or I guess I should read the whole question first, sorry. An optical system is set up with 2 lenses. Both lenses, lens A and lens B, are negative lenses. Lens A is on the left, lens B is on the right. I tell you that lens A has a focal length of 10 centimeters. This is a negative lens, which means that this is actually negative 10 centimeters, and they're both negative, so this is negative 20 centimeters. Negative lenses have negative focal points, or focal lengths, I should say, sorry. The lenses are separated by a distance of 30 centimeters, and an object is placed 15 centimeters to the left of lens A. So quick little sketch. I got both lenses. They are both diverging negative lenses. I have an object right here. That's focal length A. Focal length B, or focal length A again. Focal length B. And then going from here. So just a little sketch. Show you what it is we're looking at here. Let's start calculating. So part A, calculate the location of the final image formed by the optical system. This was the biggest part here. So what I know is that I'm going to be using my thin lens equation. And first, the light is going to pass through lens A and then lens B. So I'm going to first do this for lens A. And let's go ahead and plug in some numbers. So I know that the focal length of A is 1 over negative 0.1. Again, I'm converting from centimeters to meters right now. That is why it's 0.1 and why it is not 10. Image distance, that's what we're looking for. So DIA stays as is. And our object distance is 15 centimeters to the left of lens A. Objects on the left of our optical device are defined as positive. So we're going to say 0.15. Again, converting from centimeters to meters, and that stays positive because the object is on the left side of the lens. So, reorganizing, I'm going to subtract 1 over 0.15 from both sides. And I'm going to write DIA on the left at the same time here. So negative 1 over 0.1 minus 1 over 0.15. Again, that 1 over 0.15 becomes negative because I'm subtracting it from both sides. And I get 1 over DIA is equal to negative 50 over 3, which is then equal to DIA is equal to negative 3 over 50. Or negative 6 centimeters. And that's great and all, but that's not the final image. That's just the first image. So now I know that this first image is somewhere over here, just to the left of lens A. I know this is left because the image distance is negative. Negative image distances means that the image is on the left side of the lens. And this is a diverging lens, so we know that this should be true anyway. We should have expected this. So now I'm looking at lens B. So this new image, this image created by lens A, is going to be the object for lens B. Now, this image is not 6 centimeters away from lens B. It is 6 centimeters away from lens A. And lens A is 30 centimeters away from lens B. So my object distance for B is going to be equal to the 30 centimeter difference between both lenses plus the 6 centimeters from DIA. This is a positive value because we are considering this image from lens A as the object for lens B. So now we're looking at the object for lens B, which means it has to be a positive distance. And it is a total of 36 centimeters away. You have the 6 centimeter distance to lens A and then the 30 centimeter distance to lens B. So it has to be 36 centimeters and it is positive. So plugging that in. So I get 1 over the focal length of B. So this time I'm just writing out the thin lens equation for lens B. Again, lens B is negative. And converting to meters, I'm looking for DIB, so I leave that. And again, this is positive and converting to meters. So I'm going to go ahead and do the same thing I did in the beginning over here. I'm going to rearrange and put DIB on its own, 1 over DIB, sorry. And I'm going to subtract 1 over 0.36 from both sides. So I got negative 1 over 0.2 minus 1 over 0.36. And simplifying should get you negative 70 over 9, which, if I flip the fraction on both sides, I get negative 9 over 70, which is about negative 13 centimeters. Oh, there we go. Just barely enough room there. Almost. Negative 13 centimeters. That was the answer for part A. Part B, calculate the total power of the optical system. Use the equivalent focal length equation. So that equivalent focal length equation is power equals 1 over the equivalent focal length. And the 1 over the equivalent focal length is equal to 1 over the focal length of A plus 1 over focal length of B minus the distance between them, D, over focal length of A times the focal length of B. Plugging in, I get, and again, these are negative, so negative 1 over 0.1, and I'm using meters, negative 1 over 0.2. And yes, I'm adding a negative number here, just to show you that it is a negative focal length. The distance between them is 30 centimeters, so that becomes 0.3. And then I get negative 0.1 times negative 0. Oh my gosh. Times negative 0.2. There we go. And again, this is FEQ. And its power. So power equals 1 over FEQ equals. So if you go ahead and plug all of that in to your equation, and you end up getting negative 30 diopters. So you have 1 over what we calculated is 1 over the equivalent focal length, and we know that 1 over the focal length is also equal to power. So power equals negative 30 diopters. We use capital D. So that was part B. Calculate the total magnification of the optical system. We have 2 equations for magnification. One of them involves the heights of the object. I didn't tell you how tall it was, so that equation is a little bit useless. So we're going to use the one with distances. We'll use this one. We're also looking for total magnification. So MT for total is just equal to MA times MB. So looking for a total magnification, I'm going to get negative DIA, which was negative 6 centimeters. I'm going to leave this all in centimeters because magnification is unitless, and if I leave everything in the same units, then they all cancel out and it's fine. And DOA, my object distance, was 15 centimeters. So 15. And I do the same thing for B. I get a negative image distance on top, which is negative 13 centimeters. Oh, forgot the negative. Negative 13 over my object distance, which I believe was 36. Okay. Simplifying a little bit, I end up with positive 0.4 multiplied by positive 5 over 14. And converting these to decimals, because I think that makes this a little bit easier to see, 0.357. In total, the exact value is 1 over 7 for MT. If I convert that to a decimal, I get about 0.14. So I will accept either. And that is the total magnification. Lastly, list the salt image characteristics for both images separately. So the reason why I wrote this out like this earlier, image A has a magnification of 0.4. And image B has a magnification of 0.357. So let's write these out. Because the magnification is less than 1, it's between 1 and 0, the size is smaller. It is positive magnification, so it is upright. We know that the image distance was negative 6 centimeters here. So it is 6 centimeters left of lens A, and it is virtual. It is a negative image distance, which means it's on the left side, the same side as the object, which means it is a virtual image. Now, very similarly, image B, this is smaller. Our magnification is less than 0.4 and greater than 0, so it is smaller. It is also positive, so it's also upright. It is our calculated image distance was negative 13 centimeters. So it is 13 centimeters left of lens B, and it is also virtual for the same reasons. The image distance is negative, which means it has to be on the left. That was it for question 8, and that was it for the test. The rest is just formulas and a blank page in case you needed it on the back side of the formula sheet. Any questions, please email me. Thank you.